All right. Thanks, Ed, and thanks again, everyone, for staying. I know it's been the end of a long week. I'd like to acknowledge my co-authors, Edward Hyer and others at the Naval Research Lab, and also John Hyer and others at NASA Langley. One of our goals... So one of our goals at the Naval Research Lab is to produce regional automated forecast of smoke emissions in near real time. And this is an example of a smoke tracer built into the Naval Research Lab's mesoscale model during the fire season of 2013. And there are a variety of smoke forecasting products available. The thing to keep in mind, though, is that all of these begin with an inventory of the current smoke emissions. And those inventories are usually based on the satellite fire detections. So we're working in three broad areas here. One is how can we use these fire observations to identify the potential for the most extreme fire behavior, which is important for determining where smoke is going to go and how much smoke is being released. Also, how can we bring in weather information to help with these forecasts? And finally, how can we combine the two, the weather and the fire data, to help improve smoke emissions estimates? So most of our previous work has been focused on the Boreal forest of North America. This is a region known for many extreme fire and smoke events. There's an example here from Alaska in 2004. Most recently, we've been working on developing a 24-hour prediction of large fire growth and decay, because most smoke emissions forecasts typically assume persistent fire activity through the period, which may not always be valid. We've also been using the miser smoke plume heights to see if we can quantify potential for high-altitude smoke injection to help alleviate the problem that Arlindo was describing. And we've done this, we've compared the plume heights with the MODIS fire data, both the standard fire product and the subpixel data that Wilfred was describing earlier. But many of these fires pass through that doomsday zone, and the subpixel retrieval can be used. So we've been moderately successful at doing these things in the Boreal forest, but we've realized that if we really want to get at the most extreme fire behavior, we need to look at this in more detail. So that brings us to the 2013 rim fire. Many of you may have probably heard of this. It was in the news, mostly because it was threatening Yosemite National Park and some of the infrastructure in the area. But from our standpoint, it's important because there were two major spread events during this fire, and there was also lots of pyroconvection. As you can see here, capping PyroQ, and on two occasions, these PyroQ grew into what we call pyrocumulonimbus, or a PyroCb, which is a fire-triggered thunderstorm. So there's quite a bit of extreme fire behavior going on here. It obviously had many air quality and visibility impacts, both regionally and locally. Many locations had unhealthy air quality for days. So we're going to use this fire to get at some of the impacts from the most extreme fire behavior on smoke emissions. So this map here shows the progression of the rim fire through most of its life, and it illustrates the problem very well. We have ignition here. The fire grows steadily for a few days, and that's when the PyroCbs occur. And then there's a 2-day period here where the fire explodes in size, corresponding about 35% of the total burned area. So if you were forecasting persistent fire activity, obviously your emissions would be off. And there was a second spread event a few days later, though not quite as big. So if we look at this from the satellite fire data that we have available and the airborne data, here on this red curve in the time series is the cumulative burned area as provided by the U.S. Forest Service. They fly nightly flights over the fire, providing IR data to produce fire perimeters. And the black is the GOES fire data power. It's very similar to the MODIS product. It gives us a measure of fire intensity, and here we've normalized it hourly, accounting for how many scan times and the mean FRP and fire pixels per hour. So if we look at where the most extreme fire behavior is occurring, you notice that the two PyroCbs and the two spread events are not occurring at the same time, and that's important. We're going to look at these separately. Also notice that while there is quite a bit of FRP during the entire primary burning period, it reaches its maximum during these two spread events as compared to leading up to the pyroconvection. And the third thing we have to keep in mind is that the regional fire weather indices that are typically used for forecasting fire danger were maxed out through the entire primary burning period, there was nothing there to suggest that we would have a really extreme day over just a general day of fire activity. So the question is, can we build an improved predictor? And after looking at the rim fire, we realized that we can't ignore what's going on in the upper levels of the atmosphere. For the first few days of the fire, the area was influenced by this area low pressure that became cut off from the mean flow and was just meandering along the coast of California. And this had important impacts on what was going on at the surface and driving the extreme fire behavior. So if we look back down at the surface now from observations near the fire, here we have a time series of wind speed. And notice during the period of that cutoff low, the wind speed's increasing until you reach that first spread event. But what's really important here is that when we reach that spread event, the nighttime wind speed shown by the blue circles remains high during the nighttime, which is not typically what happens. Also, the second spread event was triggered by the passage of a transient shortwave trough that's denoted by that vertical line. So it's having important implications of what's going on at night. When we look at relative humidity, as that cutoff low was ejected through California, the RH dropped during that primary spread event. Again, 2 nights where the RH was below 35%, which really helped induce that extreme fire spread. That didn't quite happen during the second event because it was much more transient. So there are important implications here. The first is that fire weather indices are limited because they don't include what's going on in the upper levels, and they also usually don't consider what's going on in the nocturnal hours. It suggests that we should really be using a top-down approach if we want to get at the most extreme spread events. And also, if the fire activity is remaining high during the nighttime, then the amount of smoke being released at night is also higher than what you would typically assume. And Pablo Saide and others have a paper on that in GRL, and it was also covered this morning in another session. So if we look at the general characteristics of the smoke plume during these periods of extreme spread, we notice that we have a very large smoke plume, very thick, but there's very little convection in this image, just a few capping PyroCb. And the atmospheric profile is very, very dry throughout. And at the surface, it's very dry and it's unstable. The lapse rate is near dry adiabatic. This situation is favorable for producing what we call a plume-dominated fire, where an updraft is allowed to sustain itself and produce its own circulation. And then if you have disturbances moving through, this situation can be further enhanced. So also during Seekers, we were very fortunate to have observations from Seekers during the rim fire. Here you see flight tracks of the NASA DC-8 aircraft flying through the rimfire smoke plume on August 26th and the 27th. The background image is the MODIS AOD, and it shows that there's about 4 or 5 days worth of smoke emissions here. The Seekers data set itself gave us approximately 48 to 50 hours worth of smoke emissions corresponding to the second spread event. So if we use the LiDAR data that was collected on board the aircraft, we get a very good representation of where the smoke particles were in the vertical during this time. And the important thing to keep in mind here is that despite having a very intense fire and some isolated pyroconvection, all of the smoke particles here are found below 3 to 5 kilometers AGL. And they're very well mixed. The environment that I showed on that previous slide is very favorable for a deep mix layer. So this smoke is well below the 10-kilometer height of the tropopause during this extreme spread event. Now, if we compare that to what was happening a few days earlier when we had the PyroCbs, we notice now there are smoke particles approaching that 10-kilometer height. And this image is from Calliope off the coast of California, because corresponding to the first PyroCb event. So these PyroCbs are more efficient for the lofting of smoke. And if we compare that to what was going on during extreme spread, we notice that we have higher smoke particles with the PyroCb. The fire intensity is still high, but it's not quite as high as during the extreme spread. The low-level meteorology is the same. There's extreme fire danger. So it brings up the question then on what are driving these pyroconvective events, these large PyroCbs. Now, before we can answer that question, though, we have to be able to characterize the pyroconvection in some way. So we're currently working on developing a PyroCb detection algorithm at NRL. And in order to detect the pyroconvection, the first thing we need is a fire. So the red curve here is the GOES FRP that I described previously. Then we need to know, do we have convection? So we use the 11 micron minimum brightness temperature from GOES. That gives us an idea of how high the cloud tops are. So the cooler the brightness temperature, the higher the cloud top. So that's shown here by the black curve. And anywhere there's a blue circle there, the brightness temperature is cooler than the condensation level temperature. And then the last piece we need to know is how can we separate the pyroconvection from traditional convection? Well, pyroconvection has a lot of small smoke particles within it. It leads to a different droplet size distribution than traditional convection. So if we look at the difference between the 4 and 11 micron brightness temperature, it should be very large during the pyroconvection, and that's shown by the dashed black curve here. So our first PyroCb has a very, very cold cloud top and a very large difference between the two channels. The second one still has a large difference between the two channels, but it's not quite as intense in terms of its overall cloud top, so we're calling that a marginal PyroCb. I've highlighted where the pyrocumulus are occurring, but these are very small and were just identified visually. So we can use this then to separate out the traditional convection here, which does not have that spike in the 4 and 11 micron difference. And finally, if we compare this to the cloud mass data that are provided through the GOES fire mask, we can see here the higher this black curve, the more compromised the FRP data are by cloud cover. So it's no surprise that during this first PyroCb, our fire data are compromised, and to some extent during some of these other convective events. And it shows that if we're going to link an FRP value to a pyroconvective event, we have to be careful on how we assign that. But with this information in hand, we are moving forward and hoping to move toward the prediction of PyroCb events. For this, we know we have to have the intense fire. We know that we have to have fire danger at the surface. But the big thing that's missing is moisture. Where's the moisture coming from that's driving these clouds? Some studies suggest it's being released by combustion. Other studies suggest it's being entrained by the ambient atmosphere. Our hypothesis is that you're not going to have this PyroCb unless you're in an environment that's favorable for dry thunderstorms. So we're going to be looking for an approaching disturbance, advection of moisture, and instability in the middle troposphere, and dynamics that are favorable for rising motion. So here we have the meteorology occurring during the two PyroCbs. There's an animation here of the first one. So as you watch that, you can see the PyroCb develop. And there's, in both of these cases, there's traditional convection nearby. So there are dry thunderstorms occurring. And the fire is not quite near the high terrain here, but it's close. So along with having favorable surface conditions, which we had every day, if you look below here, this is relative humidity in the vertical, and this is time relative humidity. So during both of these pyroconvective events, there's a very deep layer of moisture in the mid and upper troposphere, which we don't have during the spread events. And along with that, we also have divergence at 250 millibars, so this is the top of the troposphere. So this suggests that our dynamics are also favorable for rising motion. So the overall environment is favorable for convection. So we're using this as a starting point to move forward and looking at additional pyroconvective events. But in conclusion here, we've looked at extreme fire spread in PyroCbs. We know that the extreme fire spread was initiated by the passage of some sort of disturbance, whether it be a cutoff low or a trough, something like that. And we should probably be looking at the upper levels, especially if we're doing this from a new NWP standpoint, to pick out these extreme spread events. We had a very intense fire, but no PyroCbs were observed during the spread events. With the PyroCbs, we had an environment similar to traditional dry thunderstorms. There was moisture and instability aloft, but these seem to be more important for the lofting of smoke particles, and because they didn't occur during the extreme spread events. So we're currently moving forward and trying to examine additional PyroCb and spread events. The ultimate goal is to produce a prediction for these that can be incorporated into the smoke emissions process. So before I conclude, I'll just say that a lot of what I discussed from the rimfire is currently available in a paper in BAMS. It's in early release if you go to that link there. And with that, I'll take any questions.
Thank you. Arlinda.
Quick question. Do you have any sense of how much scavenging takes place in those fire cities? How much we're actually really getting treated how this smoke actually makes up?
I don't have a very good guess on that. I'm not a microphysics expert. But every PyroCb I've seen has been very, very loaded with smoke. And sometimes you can even see that, you know, at the cloud top.
So it's essentially amount makes out.
Yes.
All right. Well, if there are no more questions, then that's the end of our session. So I would like you all